So last time we talked about soft margin SVM, and we saw that you can write this as basically an empirical risk minimization with a regularization term. So the loss here is the hinge loss, and so without this regularization, you can impose some condition on W. So for example, you can restrict the norm of W. The other approach is to add this penalty. And if you recall, this is this controls the margin. So minimizing this sort of equivalent to maximizing the margin. And so, so now you're minimizing like a trade-off basically between the two terms. So if lambda is very small, then there's not much. I forgot how we argued this, but let's say if lambda is going to 0, then we're penalizing the loss. So you're going to get something which is close to a separating hyperplane. If lambda goes to infinity, basically, this is going to be rather useless because eventually the W that you get is 0. So, but it stabilizes the solution. If lambda goes to infinity, this part is really not important. So you can have a lot of misclassified labels, but then your hyperplane is more stable. So let's see. Yeah, the point was to try to analyze this, why this idea of stability, which is saying that if I have a data set, for simplicity, we just add a new data point as well. So n+1 points, and then I fit, I train the classifier, let's say, on this data, and then basically up to from Z1 up to Zn. These are the examples that I see. And then in another case, I just switch the ith element out with this new data set, and I'm just going to use Z1 up to, so you can think of the Zi being outside here. So we switch place with, or the n+1 switches with I, so we discard this and then train on this. So if h hat n is any classifier based on this data, and then h hat n plus I, so +1 superscript I is a classifier based on this, we expect that if you're regularizing, one data point might not affect the performance as much. So that's somehow what we want to relate to, relate the two things. The perturbation here is not significant if you regularize enough. So to do that, we had this notation of the difference in loss. So the empirical loss is this ln h, and then I have this delta, which is giving me the difference in the first coordinate. So between two functions at a given example. So that's just for simplicity. And then we had this result that if you basically randomly select one of these coordinates and switch it out, so I is a uniformly distributed random index on 1 to n. If I do that, I can relate the difference in the population and empirical loss for this empirical risk minimizer to the difference in losses that I pay between these two estimators at this random Zi. But then this index here is also random. So you randomly switch things out. So this one doesn't depend on this. This guy depends on this. And the difference, basically, this is a prediction that you get. Considering this, this is the prediction that you get if you don't consider it. And the difference sort of on average controls this difference on average. So everything is like averaged out over all the randomness. And so it's not a single, like, you can't say something about a single instance, but once you average everything out, on average, this happens. So remember this is okay. Okay. So the point now is to control this difference under the regularization, and I get a bound on the expected difference in losses. So let's look at the linear classifier. So H is now like that, and I'm going to switch to my other notation for loss. So the loss between this classifier and Z, you write it as the loss between the weight and Z. And then we also write the LW, LNW. These are based on, so the population loss, empirical loss based on this version of the loss. And so the ERM with L2 regularization would be this quantity. So this is just to remind you, this is just this guy. And I'm going to call it W hat N. And I'm going to call the whole thing, let's say WN tilde. Okay, so this is the regularized empirical loss. So the key observation is that this regularized loss is 2 lambda strongly convex if LNW is convex. So we talked a little bit about this. So that's the definition of, let's say, sigma squared strongly convex function. So a function which is convex is strongly convex. Or basically this definition also implies convexity. So if this inequality holds without this term, then this has to hold for any x and y, basically. For x, y, let's say in the domain, and then alpha in 0 to 1. So this part makes it more, so it makes it a stronger inequality. So because this is non-negative, so minus something which is non-negative, this is definitely less than this first half. So something which is strongly convex is also convex. If the norm comes from an inner product, then this definition is equivalent to f minus sigma squared over n times the norm squared is convex. There's a little difference if E is not Euclidean. So this norm, for example, is L1 norm. Then these are not equivalent. So if you look at the negative entropy, this function is convex over this simplex. So this is the probability simplex. The set of all x's such that x is non-negative and summation xi is equal to 1. And infinity elsewhere. So this would be convex. You can verify this. So this, you can show that's one strongly convex relative to the L1 norm. With this definition, if you try to use this definition, it's not hard. Just if you write it, you can see that if I have something like L1 squared, first the square doesn't make much sense here. But yeah, when I do this, or the domain, this part is just 1. So this is going to be always convex for any alpha, and you can't have like something which is strongly convex for any alpha. So this is definitely not so. This is true for any alpha, but this is definitely not true for all alphas. So this type of definition is vacuous here, whereas so something which is like strongly convex, this would be strongly convex for any alpha if that was the definition. But that one works, and it's going to be one strongly convex. but for us, because we work with the L2 norm, they're equivalent, and then you can see from this construction. So if this is convex, and then L lambda norm W is added, because I can always subtract, let's say lambda. So basically LNW minus lambda, so 2 lambda over 2 norm W. This is just LNW and convex. Hence Ln, this guy is 2 lambda strongly convex. Right, from that characterization, we see that whenever you add like lambda norm squared to any convex function, the result would be like 2 lambda strongly convex. Okay. Questions? So what is the significance of strong convexity? As you can see here, sort of it says that if you subtract something quadratic, the result is still convex. So from below, it can't be worse than a concave, a quadratic function. So you have some sort of a quadratic lower bound in a sense. So this result makes it more clear. So if you have a proper, so now things are proper, which means that they're not identically infinity, closed and convex. So closed convex appears a lot in convex analysis. So the function is closed if the epigraph is closed. But just a minor regularity assumption, then the following are equivalent if is sigma squared is strongly convex. If this holds or if this holds. So this, if you look at, so we haven't talked much about convex analysis, but if you've seen convex analysis, so you know what this means. Anyone knows what this notation here? Yeah, it's just a subdifferential. So the set of subgradients. And so we're saying for x in the domain of the subdifferential, so any point in which the subdifferential is a non-empty set, and any g in the subdifferential of x, which is like saying that the g is a subgradient at x for f, and for any y, this inequality holds. So this inequality, so if you ignore this part, this holding for any y is the definition of subgradient. Okay, so g is a subgradient for f at x if this inequality holds for any y in the domain. And convex functions have subgradients because convex functions are lower bounded by, so this is an affine function. So if you have a convex function, you can always find an affine lower bound. So this is saying that the function fy can be lower bounded by an affine function at x. So convex functions generally have non-empty subgradients. What this is saying is that I can add this quadratic term as well. Still, it's going to be below. So this is just characterizes that I can, at any point in the domain in which there is at least one subgradient. There is this quadratic lower bound. Okay, and this one is also equivalent. This is saying basically that the gradient is. So this side would be 0. That's the holds for any convex function. It's saying that the gradient as a map is a monotone map. And this is just saying it's a little bit more than that. So it's like strongly monotone, something like that. So we're going to use the characterization too. So you can see from, again, the definition of the subgradient where if we ignore this. So if you ignore this part, you can see that for a convex function to have a minimum at x is equivalent to there being a 0 subgradient in the subdifferential of at x. So x is a minimizer of f for a convex function if there, actually this is in general true, if x is a minimizer of f if 0 is in the subdifferential of x, if and only if basically. And so if you plug this into this, this says that at the minimum, so if x is the minimizer, then the deviations of f are controlled by the deviations in the input. So this is very important because you can translate, so this is like a curvature bound. So if I know a perturbation, so if I perturb x to y, and I see that the function changes this much, I can multiply by 2 over sigma squared. I know that the inputs have changed by the square root of that much at most. So this is the key inequality that holds around the minimizer. So this was like a short detour. Any questions? Okay, so here's the result. So if this loss function is convex and it's also row Lipschitz, so in the first argument, the weight basically is row Lipschitz with respect to the L2 norm, then we have these inequalities. So this W hat n plus 1 I is the weight that I get by just swapping the n plus 1 with I. And this is the original weight. So the difference is controlled by this. And you can see as I increase lambda, this difference gets smaller. And also that the delta loss is also controlled by 2 rho squared divided by lambda n. And again, if I increase lambda, this goes down to 0, which is saying that regularization sort of stabilizes things in a sense. And if lambda is 0, you can see there's no bound basically. So this bound is not useful if you have no regularization. So to prove this, I first note that if you look at the Ln plus 1 I, so this is the loss with the ith data points swapped with the n plus 1 point. This is the original loss, and then I add and subtract this piece. Okay, so remember these are just Lnw is the sum. So just maybe write this down here. So Ln W is 1 over n summation I from 1 to n LWZI, and Ln plus 1I is just summation I from 1 to n I belonging to basically, let's say J. Should use J here. J from 1 to n plus 1, except J not equal to I. We just remove that. So if you look at the difference is just that this guy has LWZN plus 1 and the other one has LWZI. So that's the difference. And then I'm going to define the regularized version of this similarly, the Ln plus W. That's just the unregularized version plus the loss. Similar thing we defined for this. So this plus the loss is Ln tilde W. And so the difference between the regularized versions is also the same because the regularization term is the same. So we have this inequality. Then we write our one form of a basic inequality. So that's the basic inequality. Anyone wants to justify why this inequality is true? Yeah, great. So this W hat n plus 1 I is the minimizer of this loss, and there's no feasibility assumption. So W hat n is any other thing. So the loss is at least as good. The loss of this is as good as the other one. Then we subtract the, or basically you replace this guy with this expression. Okay. So if I replace this with that expression, you can see this is the inequality that I have. So this side turns into this plus this guy, and this side turns into this plus this guy. So let's check whether it's true. Yeah, you just have to look at this deviation. I'm just evaluating it W hat plus 1 I, and then on the other side I'm using the same, but with W hat. It's the same sort of formula used twice. And then we rearrange. So you move things around. This L until that comes. So we move this to the other side here. And so I get this. And then we move this guy to the other side. Combine it with the two. So I get this guy minus this, which is the delta L W hat n plus 1 I, and then minus or plus actually plus this guy minus this guy, which gives me this. Okay, so if you just consider the signs and things like that, hopefully this is correct. right? So that's what we get. So you can see the regularized, the difference in the regularized loss is controlled by, like, it's at most 1/n times these like little losses, like the small, basically delta losses. So that's the property of the regularized loss. I believe this is also true. So up to this point, I think everything is true, even if we do it without the regularization. Okay, so things would go true. But the point is that this is the minimizer of the regularized. So this is only true. So if these were unregularized versions, and these were the minimizers of the unregularized version, it seems like this still holds. Just keep track of where we use regularization up to this point. Even if lambda is 0, you're fine. Then you're going to use the row ellipsis assumption. Okay, so this assumption implies, it just implies this, because again, remind you that this is nothing but L W and Z minus L V and Z. So this is bounded by rho times W minus V. So what do we get? So if I apply this, where should I apply this? So I'm going to apply this to that equation, like inequality. I get W hat n plus 1I minus W hat n. This is going to be bounded by basically 2 rho over n W hat n plus 1I minus W hat n. Right, so the thing is, these two, they have different sort of z's in the, like the third coordinate, but the difference is the same between the weights. So the two weights involved. So if I apply this inequality, triangle inequality, use triangle inequality, I get twice rho divided by n times that. Right? I have this, and then I have this lower bound. So where does this come from? That comes from the strong convexity. Okay, so if you have, if you take the deviation relative to the minimizer, that would happen. So this is, so you can see this guy is the minimizer of Ln tilde. This is not, this is some other point. So this is like Fy minus Fx bigger than or equal to like sigma squared over 2 y minus x squared. That's the equation. So that holds. So now this side is definitely lower bounded by lambda deviation of the weights squared. Lambda W hat n plus 1I squared. So this is going to be lower bounded. And then if you just look at this, it's just this, yeah, there's a 2 missing here. So 2 rho over n. And then one of these powers cancel out. So I can cancel this with this thing, right? So I get this first inequality. And then the second inequality follows from, so how do we get the second inequality? You can get it from the first. Yeah, so this is Lipschitz basically. This guy is lower bounded by rho times W hat n plus 1I minus W hat n. So if you combine it with 6, then you get that. Okay. Questions, comments? So did we use the fact that these are regularized solutions? Right, okay, so that the only thing that, yeah, so here, so that uses, used regularization here. So without that, I couldn't, I would still have this one, but I can't relate it to this deviation. So that's the key that allowed us to do that. Okay, so we have this result. Questions? So now I can combine this. If you go back to this result, now I can conveniently combine these two, and I get a very nice bound on. So this left-hand side doesn't depend on this swapping the coordinates, so I just get a nice bound on the difference in the empirical and population loss for this. So that's what we get. So this quantity here, the expectation is over the training, and we know from that lemma that this is bounded by this, where I is again random, but we saw that this holds for any. So this holds basically for any z and any I. So this is like a uniform bound for any z and any I. So if I just replace z with z sub I and then capital I here in the superscript, so even if things are random, this still holds. And so the expectation is also true. So this would give me just that from the second inequality. Okay. So this is an interesting bound, is saying that the expected population loss minus the empirical loss for the regularized weight is controlled like this. Okay, we use convexity and row Ellipsis assumption for the loss, and we got this nice result. Any question? So there's still one more thing that we can do here, and what I want is basically this expectation. I would like to have the expectation of L W hat n. I want to bound on this. I can write this as the expectation of L W hat n plus the expectation of right? So the second term is bounded by that theorem, but the first, sorry, Ln. So this is saying I have the empirical loss I have the empirical loss of W hat n expectation, and this is the deviation. So this deviation we can control, just controlled by stability arguments, bounded by 2 rho squared lambda over n. So the question is, how do I control the first term? So the thing is, W hat n is a regularized solution. I don't know much about what happens for the loss itself, but I know what happens if I add. So I can add the regularization back. Right, so this is bounded by this from above, right? Now we know this is just basically this is Ln tilde W hat n. So now what can we do? we can say that this is bounded by this for any fixed w, right? Because this is the minimizer for any fixed other w. This is an upper bound on this. And so I get this equation. And then because the expectation, so there's like the ln w plus the norm. So the expectation, because we're evaluating it at a fixed, so w is a fixed, is a deterministic quantity. What I get that is that this what would be the expectation? Can you simplify this? Goes away, yeah, basically. So if you recall, this would be just, what would it be? So remember, Lnw is just 1 over n summation I from 1 to n Lw zi, right? So when I take the expectation goes inside. And this is just, all of them are the same. So I get the expectation of, let's say, L, W, and Z1. So that would be just L, W, right? It's the population loss of this. So I get LW plus just lambda, norm W squared plus 2 rho lambda n. And this holds for any W. So I can just take the infimum or whatever. Yeah, H is not necessarily good, but yeah, so let's say H is, we identify the function class with the weights. So I'm minimizing over whatever class that I want. So you're minimizing this bound. And so this gives you, because it holds for any W, it holds for the minimum. And so this gives you the so-called an oracle inequality. Okay, so it's an oracle inequality. So why is it called an oracle inequality? Sorry? It's actually because so if you want to optimize this, so let's say I can pick, let's say the best, so what I would like to find, I want to say that the L of W hat n is close to L of W star, where W star is the minimizer of LW. So suppose W star is the minimizer. If I plug this in here, I get LW star plus this extra term. And then I have to choose lambda properly. So in order to choose lambda, then I would need, so this could be like LW star plus lambda W star plus 2 rho over lambda over n. So in order to optimize this bound, I have to choose the right regularizer, because you can see if I increase it, this term goes up, this term goes down. So there's a balance. And the optimal choice depends on the norm of W star, which I don't know. So if an oracle gives me the proper norm, then I can choose. So optimal lambda depends on norm W star. So what would be the optimal lambda if you want to choose the lambda? Let's say W star is a small number. We can pick it to be the smallest possible. Then I would have this. So how should I choose lambda? I have like a lambda that I can minimize over. Yeah, that would be it. But in these cases, the simplest thing to do is like also the true, like if you take the derivative set equal to 0, it's equivalent to setting these two terms equal. You can just verify this. So the optimal lambda would be by equating the two terms. So lambda would be root 2 rho squared over norm W star n. Something like that. Okay, and then you plug back in, the two terms are the same. So the bound that you get is what do we get? LW star plus so if you plug back in here, you get one W star comes out, and then effectively you would get 2 because these two terms would be the same, and then W star root rho over 2 rho over n, or like it would be basically root 8 rho squared W star squared over n. Okay, and so if I don't know this W star, what I can do, so this is the result that you can state for the soft margin SVM. So we know, so let's say X is in rho times, so the space of examples are bounded. So this is saying so X is a subset of all X such that norm X is less than or equal to rho. And if this is the case, then the hinge loss for the SVM, so the hinge loss would be LWZ, would be 1 minus Y inner product W and X. Right, and is this rho Lipschitz? So let's call this phi of W YX. So LWZ minus LVZ is phi WYX, right, minus phi W, sorry, VYX. So phi is, for the hinge loss, it's 1 Lipschitz. Okay, so we get WYX minus VYX. And so this is by Cauchy-Schwarz norm YX, which is norm X, times W minus V. So if I bound the norm of X to be like rho, then this would be the hinge loss applied to this. So there's like a composition of the hinge loss and this linear function. That would be rho Lipschitz. So it satisfies the assumption that we have. And then I would get a bound like this. So this holds for any W star. And so if I restrict myself to, I can take the infimum or all W stars for which the B, like the norm is bounded by B, and this penalty would be like this. So if I can choose this B large enough, so for example, if there exists a very good solution whose norm is bounded by B and the hinge loss is very small or 0, then I get that this goes down like rho squared B squared over n. So no dimension dependence sort of, but there's a dependence on the norm of B. So that's the kind of result that you can show. And the same upper bound holds, but this side is the same, but the upper bound on the L01 loss is the same. But it would be in terms of the best hinge loss, not the best L01 loss. Okay. Questions? So this is, if you compare this is similar in a sense to the, so like 8 rho squared b squared plus n. There's this part which is not going to go to 0. This is like, it's like there is some sort of a, like there's a base risk, right? So the ideal thing is like if you had the L01 here and then minimized over all the possible W, that's the best 0-1 loss that you can get. This is comparing that to the best. But the best here is not 0-1, it's like hinge, and there's also this bound. So if you can assume that there is like a hyperplane that, so this is similar to the margin bound. So if you recall, you can see there are some similarities with this result that we had. So this part, so there's a 0 here because the 0-1 loss is sort of ideal 0-1 loss is 0. But then there's like rho divided by gamma squared. So now here we have rho squared b squared. So b plays the role of 1 over gamma. There's no margin here, but the norm of W plays the role of that, and rho is the same. So we assume that these guys are. So the rho is the same, but you don't have a margin, but the norm of W plays the role. So if you compare qualitatively, it's a similar bound, but there are some caveats in the sense that you're not comparing with the best L0 norm, but the best hinge norm, but that's sort of expected because you're not minimizing the L0 loss, you're minimizing the hinge loss. So this is not, it's a quite nice result, okay? And the technique was interesting. One of the things is that this is like an average case. So this argument doesn't give you like high probability bound on the hinge loss. But because of the technique that we used, there was a lot of averaging going on, so you get a bound on the average population risk. Questions? Okay, so now I want to like wrap up the discussion of SVM. So let's talk a little bit about, so we have some good understanding of the performance of the hard and soft margin SVMs. The main idea was if you bound the, like you bound the X domain, and then you have some sort of margin bound or like bounded W. If you're like working with bounded W, then you can get like generalization sort of errors that go down like 1 over root n. And then there are these factors that don't depend on the dimension. So they control like that. So that was like the theoretical take-home message. And this suggests that you might be able to like move on to like infinite dimensions, and these results still hold. And so that's what I want to sort of build towards. But I just want to motivate that SVMs give a very nice motivation to kernel methods. So let's talk about some interesting aspects of SVMs. In particular, because let's look at the hard SVM. It's a simpler problem. You can do the same for the soft SVM. Because it's a convex problem, and if you have sync convex analysis, there's a dual problem. And usually when you look at, so this is called the primal problem. There's a dual problem which involves a dual variable. It's another optimization problem, and together these two optimization problems are very much related. So if you solve the dual, you can solve the primal and vice versa. Sometimes you try to solve them both. So it gives you a lot of information about both problems, and also like allows you to like expand the space of solver. So you can, when you try to solve this, you can solve the dual, there's sort of there's a lot of sort of interesting interplays between the two. So the way to write the dual, the easiest way that I know is to, so if you have these constraint inequalities, inequality constraints, what you would do is try to write this in the standard form. So if you're minimizing a convex function, you usually write this as like a convex function less than or equal to some 0. Okay, so it's like gi of w is less than or equal to 0. So the problem is minimize FW subject to GIW less than or equal to 0, I from 1 to n, and F and G1 up to Gn are convex. So this is a general format of an inequality constraint convex problem. What you do then is you form the Lagrangian. And the way to see this is that I can write this as min, or let's say inf over W. And then do it somewhere else. Sorry. Let's do it above here. So what we can do is we can write a dual. So how do we write it in a form which is suitable for driving the dual? Let me ask you guys. Anyone recalls? I want to write it as inf soup over some variable. So how do we write this? Right. So you'd add the Lagrange multipliers like alpha I, GI, W, I from 1 to n. Soup over alpha I is being coordinate-wise bigger than 0. So to see that this sort of gives you the same problem, if I first minimize over alpha, sorry, if I want to optimize over alpha, this term, the first term is fixed. So I have to optimize this linear function. And if GIW for the fixed W, GIW is negative, right? The best that I can do is that alpha is 0 for that. If GIW is, so it's less than or equal to 0, the best is alpha equal to 0. If GI is strictly positive, then I can let alpha go to infinity. So this would blow off, so it goes to infinity. So then when I want to take infimo over W, I don't consider those W's. So this effectively encodes the constraint. So because later on you want to minimize for all the W's for which this thing is infinite, you don't have to consider it. So this is saying that we only consider the cases, the W's for which this is non-negative. So that's an exact inequality, like equality. So this problem is equal to this. Okay, and then it's not hard to see that this is lower bounded by, if I interchange the soup and inf, I get a lower bound. This is called weak duality. So this is weak duality. This always holds. Inf soup is bigger than soup inf. But if this is equality, good things happen. So then we have, then we say that a strong duality holds. So under some conditions on the optimization problem on these functions, then oftentimes strong duality holds. And so I can write the problem equivalently as, so if I call this, this is called the Lagrangian. So this would be LW and alpha. So the primal problem is, the original problem is inf over W soup over alpha bigger than or equal to 0, L W on alpha. Assume the strong duality holds, then I have the soup over alpha, inf over WL, W and alpha. Okay, and this is sort of an interesting inequality. There are conditions for it. One thing that you can prove is that, so if the Kkt conditions sort of hold, Kkt conditions means if there is like a W star and alpha star, such that W star is the minimizer of L W alpha star over W, so this function. And if alpha star is the maximizer of alpha maps to L W star alpha. So if I can find a pair, this is called the primal dual pair. And then W star is primal feasible. Alpha star is dual feasible, in this case non-negative. Primal feasibility here is just vacuous. So if there exists, so these are called Kkt conditions. If there exists a pair that satisfies these four conditions, effectively the first two is saying that this pair is a saddle point of the Lagrangian. So if I fix one coordinate in one direction, I'm going to go down everywhere as I move from that point. If I fix the other coordinate, I'm going to go up. Like here, I'm going to go up. Here, I'm going to go down. So it's a saddle point situation. In one direction, it looks like this. In the other direction, so the function looks like this in this direction and this in the other direction. So you can imagine what the saddle point is. So if these conditions hold, then for example, the first two would, and obviously this have to hold. This gives you a strong duality. You can show this holds. So sometimes you write the Kkt conditions. If you can solve this, you also know that the strong duality holds. This is not hard to show. But there are some other conditions besides trying to solve the Kkt conditions that give you like immediately that this should hold. In any case, we'll come back to this and discuss it. So this is called the dual problem. So in our problem, it holds. So what happens is that if you do it, in our case, I have to first solve this. So driving the dual. How do I minimize over W? First, we have to find this dual function. It's called dual function. So this is in our case inf over W. This plus, I have to rewrite these like that. So I would get plus alpha I from 1 to n. 1 minus yi W transpose xi. So how do we minimize over W here? There is no constraint on W. Take the gradient, yeah, set equal to 0. This is basically a simple quadratic problem. It's like this minus W transpose Z. Like the summation, the first summation, this doesn't depend on W. And if you multiply, it's just W transpose times Z, where Z is just, so take Z to be summation alpha I, yi, xi, right? So we're minimizing this over Z. So what will be the solution? Take the derivative. Minimize over W, sorry. What is the ideal W? It would be Z, and then you plug it in, you would get negative 1/2 Z squared. Right, so also remember, so if you fix alpha star, like alpha star here, the minimizer of W would be just this guy. So that's the first of the Kkt conditions if you later want it. So minimizing the Lagrangian at a given alpha is equivalent to just setting it equal to Z. So W star, so let's say W star, which is argument of L W alpha star, is just equal to summation I from 1 to n alpha I star yi xi. So that gives me the first of the Kkt conditions. So W star has to be equal to this. We'll come back to the other case later. So this is just a little side note here for future. So this thing it turns out to be just negative 1/2 summation I from 1 out to alpha, 1 to n, alpha I, yi, xi. And then, so the dual problem is just max or soup. You can write it soup over alpha plus bigger than or equal to 0 of this dual function, right? Call this phi. So there's this part which comes out. And so this has to be summation alpha I from 1 to n. So I get alpha I from 1 to n minus 1/2 summation I from 1 to n alpha I, yi, xi squared. Okay, so that's the dual problem. It's another convex problem. Questions? Let's go down here. Yeah, so that's the dual problem. And then so we can solve this for alpha. And if you have that alpha, the primal solution actually follows from this little calculation that we did here. So there are two comments here. One is that if I expand this quadratic here, I would get something like this. Right? And you can see that it only depends on the inner product, pairwise inner product of xi and xj. So if I put them in a matrix, this is called the Gram matrix of the examples xi's. And so to solve the dual, so to solve the primal, you need the xi's themselves. But to solve the dual, you don't need to know the xi's, you just need to know the pairwise inner products. And you can see also that, so this W is in RD, where D, so our xi's are like in RD. So this dimension could be very large, but the dual is always like n-dimensional. So the dimension of the dual variable is equal to the number of constraints that you have. So even if this is very high dimensional, the problem that you have to solve is like in n dimensions. And you can see which one is better. So if D is very small, solving the primal is much easier, probably. Not necessarily much easier, but like, it's like you're optimizing a smaller space because the many constraints probably is not that easy. But the dual is useful when D is large. So instead you would solve something like this. Yeah, I should take that back. Which one is easier is a little tricky. But then for the dual, you don't also need to know xi's themselves. You just need, or even you don't need to store them. You just need to know the pairwise inner products. And then once you realize that if I started from something like this, I had a feature map phi that mapped, let's say, the original x space x to some r, I don't know, k, actually rd. So x could be even higher dimensional. Oh, sorry, x is not higher dimensional. Let's say x is smaller dimensional, and then I map it to a higher dimensional space, rd, so that in the higher dimensional space, I have the separability. So we talked about this, for example, if you have x1 and x2 in R2, so that's your two-dimensional case. And then the feature map might map it to like 1, x1, x2, x1, 2, x1, x2, x2, 2. So a linear separation in this feature space would also include things like separation by circles or ellipsoids and things like this. And you can go to higher order polynomials. So if I assume I have separation in that space, I can solve the SVM under these constraints. And you can see that if I write the dual, basically phi xi's are now my new xi's. So what I would get here is the inner product of the phi xi and phi xj. And you can call this a kernel. This is going to be, if you have any feature map, you can define a bivariate function on, so this is so k is a bivariate function in space x to x to r. If you have inner product in RD, which is just, let's say, usual product in RD, right? So this space x could be even abstract. It could be like non-Euclidean. You map it to RD, and then you take the inner product in RD. So this defines a symmetric bilinear form. Not bilinear, sorry, symmetric bivariate function, and it turns out to be also a positive definite function, and so these things are called kernels. And so what you're effectively doing is that you're replacing this inner product, which is a particular kernel, with a general kernel, and this is called the kernel trick. And you can see in the case of the SVM, by going to the dual, you can kernelize the problem. And then you don't have to worry about what this feature map is, just as long as you specify this k, like equivalently, there is some feature map that's doing this for you. And this just simplifies the problem a lot. There's a lot of machinery in the background, which is just encapsulated in this k. But that's something that we were going to talk about next. So what are these, what do these kernels sort of represent? I mean, what we can say about this? So that's one comment about the dual, or one feature from the dual that you can easily see. The other feature is, if you go back to so any questions about this? No, okay. So if you go back, online people, feel free to ask questions. If you go back to the Kkt conditions, the things that I mentioned, the minimizer for this one, usually what you would get is, so the Lagrangian is, it would be like, remember, f w plus summation alpha I from 1 to n. There's going to be a star gi. So if things are unconstrained, usually you set it equal to, like, take the gradient and set it equal to 0. So this would be equivalent to trying to say that w star satisfies these equations. So if things are differentiable and there's no so assuming differentiability and w star being in the interior of the, it's like in the interior. Interior of the, like, the primal domain, then this has to hold. So this is going to minimize this if and only if, because we are dealing with convex functions, if and only if this holds. And this is what we did, actually. So in our case, this turns out that w star that looks like this. So that's the first of the Kkt conditions. The second one is simple, because I want to maximize over alpha star. And you can see from here, when I fix, so this is saying maximize, this function is basically f w star plus summation I from 1 to n alpha I gi w star. And I try to maximize over alpha star. This part is fixed, right? I have to maximize over this. And in order to, so how should we maximize over this? So if w star is feasible, so if this is, so if w star is feasible, these are going to be what? These are going to be strictly less than or equal to 0. Okay. Right. And so the maximum, like if you have a function which is, so these are non-negative and this is negative. So you can imagine if you try to minimize something which is like a positive times something which is like non-negative times something which is non-positive, the maximum is where this is exactly 0. Right? Otherwise, if this is strictly negative, then because it's positive, this could be negative up to like 0. So when you try to maximize this, assuming that the feasibility holds, primal feasibility, then each individual term has to, so this minimizing, maximizing, this would be equivalent to alpha I GIW star is 0 for all I. Right, so that's the second Kkt condition. So the maximizer, this is the saddle point condition, implies that these have to be, each individual will have to be 0. In our case, this means that, and so this is called complementary slackness. So what essentially says that if the constraint is active, which means that these GIs are strictly less than 0, then alpha I has to be 0. If it's not active, if it's not active, it has to be 0. If it's active, which means that GI star is 0, GIW star is 0, then alpha I star can be. So you can see it here. So if the constraint is active, then this is 0. This doesn't tell you anything about alpha I star. But if the constraint is not active, which means that if yi, so this is less than or equal to 1. So it's not active, it's strictly less than 1. If it's active, it's equal to 1. So if this is the case, then it implies that alpha I star is 0. Okay, so together, these conditions tell you that W star looks like this linear combination of like yi, xi, and then the coefficients are only non-zero if the constraint is not active. Okay, so basically, it's only, so this W star is a linear combination, let's say xi's. Xi's are the vectors, right? Yi's are just signs. The W star is in the span of xi's for which yi W star xi is 1. Okay, and then it's easy to, if you recall, so the distance, so yi W star xi divided by this. This is the distance of, like the example, xi, yi from, let's say the distance of xi, distance of xi from the hyperplane, from the hyperplane. Like identified by W star. Okay, so for these points for which this is equal to 1, this is 1, right? So for all these examples that support W star, the numerator is 1. So only the points that are at distance 1 over norm W star control the W star. Okay, so this is like the notion of support vector. It's called it's called the support vector mesh, right? Because only like at the optimality, there is this hyperplane that passes through these points, and all the points that are sort of you can see this is also the smallest. There's nothing. So the points that control this all have the same distance from this, and the other points sort of are not important. They're further apart, and they don't influence this. The only thing that there's some sort of robustness. So if I perturb these guys that are away from the hyperplane doesn't change as long as these support points sort of remain the same. So it's like this nice geometric idea, which just follows from if you write down the Kkt conditions. And then you can extend this idea to SVM. The dual will be a little bit more tricky. They can like write down the Kkt conditions. I'm going to skip this. You can do it for yourself as an exercise. And then the Kkt conditions would be a little more involved because you have two sets of inequalities. So you have two sets of dual variables. And then there's some examples that are inside the margin and things like this. So there are some interesting, nice geometric ideas that go with it. But the essential idea is clear in this case. Okay, so that's the essential point of the SVM. So this wraps up our discussion of the SVM. I think we had like a good a collection of topics about SVM. So they are nice empirical risk minimization procedures. The Soft-SVM, you can think of it as like minimizing the hinge loss. It's like a relaxation of the L01 loss. We saw that you can get dimension independent bounds if you have margin conditions in the separable case, or if you have bounded assumption, you can still get dimension independent sort of oracle inequalities for the Soft-SVM in average sense. And then we saw this dual, and then the solution, why it's called support vector machines. And so there are more to it, but the next topic that I want to talk about and come back to next time is this kernelization idea. So what we're effectively doing if you do this is that we're sort of moving away from linear functions. Basically, it used to be like w times xi was a linear function, both in w and xi, but it was a linear function in xi. Now we have like a more complicated function. It's a nonlinear function. The function class that you're looking at is the sort of the RKHS, the producing kernel space of the kernel. And so that's what we're going to come back next. And so I'm going to start with some like basic, very basic review of a bit of functional analysis to be able to like say something more rigorous about these things. Okay, sounds good. Okay, thank you guys. See you next time.